Welcome back to differential equations. In this video, we're going to be talking about second order differential equations. And we're going to be doing things a little bit differently than I do in most of the lessons in most of the math classes I teach. Before we dive into the theory of how to deal with second order differential equations, I wanted to talk a little bit about why they are so important. Most students who take a course in differential equations are going to continue onward in a career in physics or in engineering. Occasionally, mathematics, computer science, chemistry. Every now and then, somebody who's interested in biology or in finance and economics. But by and large, most students who take differential equations are going to go on to physics and engineering. And if you're going to do physics or engineering, then one of the things you need to be very familiar with is Newton's laws. There are three laws of motion, and the physics behind them is not interesting because this is not physics class, this is mathematics class. But the formula F equals ma, force exerted on an object is equal to the mass of the object times the acceleration. Or another way of writing that, or another way of saying that, if you want to know how the object is going to accelerate, then you take the forces acting on the object and divide them by the mass of the object. And thinking back to the brief mentions of kinematics that keep showing up in a calculus course, because Isaac Newton is responsible for a significant part of the invention of calculus, it makes sense that a lot of it is wrapped around the ideas that come up using Newton's laws of motion. If we call the position of a particle x of t, when we introduce the idea of derivatives, we realize that x prime of t is the change in position over time, which is the velocity. And then x double prime of t is the change in velocity over time, which we call the acceleration. We could keep going, right? The third derivative is called the jerk. The fourth derivative is called the snap. The fifth derivative is the crackle. The sixth derivative is the pop. But in classical mechanics, position, velocity, and acceleration actually tell you everything that you need to know. Or put another way, the fundamental idea of classical mechanics is that if you know the positions and the velocities of everything in your system, then you can predict precisely how the system will evolve and how those positions and velocities are going to change. And we do that through means of the acceleration and the force. So the forces acting on an object can depend on the position of the object, they can depend on the velocity of the object, and they can depend on time. All right, so force is a function of position and velocity and time. Acceleration is x double prime. And suddenly, we have a second order differential equation. x double prime related to x and x prime. And I got a little bit ahead of myself. I apologize. Little f is just big F divided by m, because having that extra factor of m makes things messy and we can ignore it. That also gives us something that looks more like the mathematician's definition of a second order equation instead of the physicist's definition of Newton's law. All right. So again, this is not a course in physics. I'm not going to ask you to do the analysis of forces in order to write down these equations, although it is something that is very interesting. And if you want to talk about that, I'm happy to go on about it in depth. But my big thing is going to be sticking with once we have them, we know what to do with them. And so I want to talk a little bit about the kinds of forces that you might experience that have these kinds of effects. I'm going to start off with the simple example of a mass on a spring. That is going to be our go-to situation here. All right, so if I have a fixed surface like a ceiling, I have a hook on the ceiling, I have a spring on the hook, and I have a mass on the spring. Alternately, I have a slinky. If you take your spring and you pull it down, it is naturally going to go back up. The force on the end of the spring is a function of the position of the end of the spring. If the end of the spring is closer to the top, there is a force that goes downward. If the end of the spring is far away from its resting place, there is a force that pulls it upward. And the further away you are, the more force there is. That's known as Hooke's law. Again, the specifics, the mathematical formulation of it aren't that important. I will be basing problems around it, but I'm going to give you the mathematics in the problems. Right, so but there is a force that depends on position. So we have that part taken into account. A force that depends on velocity is something that you've almost certainly experienced and never thought of. I want you to think about sitting in a swimming pool or a hot tub and dragging your hand through the water. The faster you try to move your hand, the more the water drags you back, slowing you down. That's known as the drag force. Sometimes Bernoulli drag, but again, specifics well beyond what I care about in this course. But that's something that will affect that. As you try to move, the faster you try to move, the more you get slowed down. If you move slowly, you can move very efficiently and you barely notice a drag. If you try to push, the water gets pushed away, it doesn't distribute nicely, and it takes a lot more effort to push through. Time dependent is a little bit more awkward to think about until you introduce yourself into the situation. So again, going back to the spring. If the spring is chilling out and doing its own thing, then nothing is happening. If I show up and I smack the spring, all of a sudden it starts doing something. If I set up a motor that smacks the spring at regular intervals, then the spring is going to start oscillating. And if I time it just right, then the amplitude of the oscillation is going to increase. Think pushing somebody who is sitting on a swing. If you push them at the right time, they go higher and higher every time. If you push them off cycle, you really make a mess of things. Right. So those are some very simple ideas on the kinds of things that can show up. Again, if anyone is interested, I love talking about the mechanics there and where the mathematics comes from. It's one of the things that I really adore about the study of physics, but it's well beyond the scope of this course, so I'm not going to get into it in any of the problems that you're going to see here. For anyone who is not going into the study of classical mechanics, um, what I can tell you is that we love using springs as an example because everything is a spring. If you are going to study electricity and magnetism, the electric circuits, the way that electrons move in an atom and move between atoms, is a spring holding the electron in place until you break it and then it goes away. If you are going into chemistry, you have a lot of the same ideas going on. If you're going into economics, there is a balance point, supply and demand. If things get pushed too far onto the supply side, that will change the price and the value, but it will slowly make its way back to an equilibrium. If the demand gets too high, it's going to cause the opposite effect, and then it's going to slowly make its way back. Even in sports statistics, I'm a fan of hockey, and one of the advanced stats that is used in hockey is called PDO, which is a measure of how lucky a player is being. If they are scoring more goals than expected, they get a higher PDO. If they are scoring fewer goals, letting more takeaways happen, they get a lower PDO. And the interesting thing is that for most players, like 99% of players who have made it to professional hockey, given enough games played, PDO goes to 1. And so it's another spring. If you go further away, you get pulled back. If you go further below, you get pulled back. And so there are a lot of things that can be modeled using springs. So even if springs themselves don't seem like something you're going to spend time with, if you're not going into mechanical engineering or you're not going into studying classical mechanics, it's still worth understanding because you're going to be able to build on it in a number of different ways. All right, mathematically, if we have a spring force, which is K times X, and we have some drag force. Again, there's a lot of different ways that drag can show up. For reasons that I don't feel like getting into, we use the Greek letter beta as the coefficient for drag most of the time. But that's going to be some multiple of the velocity, probably some fraction. It's a conversion factor. That's the only thing that matters. Um, and we have some applied force G of T. Well, putting these in, the total force acting on this object we get equations that look to be in this form. Thinking about the ways we've dealt with equations in the past, this is a linear second order ordinary differential equation and furthermore, m, beta, and k are all real numbers. There's no t dependence on them, right? The way that a spring behaves doesn't change over time. How far you are from the equilibrium point changes, which causes a change, but it's just a change based on how far away you are. Likewise, how hard it is to push through water doesn't change over time. It depends on how fast you're trying to go through the water. So m, beta, and k are constant coefficients. And again, that's going to be one of our big value points. All right, so we're looking to find ways of dealing with linear second order ordinary differential equations with constant coefficients. And that is a simplification of what we were doing before. I hope that I have convinced you that it is a simplification that is worth studying. Right? We will study equations of this sort in general in this course, and looking at ways of dealing with g of t itself is going to be one of the big things we have to deal with. The more complicated g of t is, the harder it is to solve an equation like this. And that's the reason that we're going to start with the most straightforward option, the simplest function that we possibly could have for g. G of t is constantly equal to 0. But again, that is still something that is very valuable in the real world. Going back to grabbing my slinky. If I have my slinky and it is sitting here doing nothing, then a differential equation modeling it is kind of boring. If I take my slinky and I stretch it out, now I have some interesting initial conditions. And the moment I let go, there are no forces, or there's no applied force on the slinky. It's just gravity and the oscillation. That's all that's happening. And so that is what the model of g of t equals 0 looks like. Right? This is much more of the mathematics works out nicely, then the physics works out nicely, that it gets its special name, but there is still physical meaning. There is still a reason to study systems that look like this. So in general, if I switch away from my flavored coefficients and I just look at A times x double prime of t plus B times x prime of t, I don't need that extra. Come on. There we go. Plus C times, why am I doing that? C times x of t equals 0. This is a homogeneous linear second order ordinary differential equation with constant coefficients. And now you start to see why we call them ODEs instead of ordinary differential equations each time, because naming these things gets to be quite a mouthful very quickly. All right. That takes us to the superposition principle, which is again one of the most important ideas in physics and engineering, especially in electrical engineering and in quantum mechanics. Superpositions are everything in those disciplines. But the idea of superposition is fairly straightforward. If you have two functions, phi1 and phi2, so that they are both solutions to a homogeneous linear differential equation, it doesn't have to be second order, it doesn't even have to have constant coefficients, then a linear combination. And a linear combination is any function x of t, which can be written as a constant p1 times the first function, plus another constant p2 times the second function. Anytime you do something like that, for any pair of constants p1 and p2, you get a new solution. And that's kind of a big deal. So I want to prove that to you in general. Well, I'm not quite going to go in general. I'm going to prove that this is going to work for any linear second order homogeneous ordinary differential equation with constant coefficients. So let's assume that phi1 and phi2 are both solutions to a times x double prime plus b times x prime plus c times x equals 0. And here, again, you also start to see why we suppress the of t everywhere when we're writing out differential equations, because these things are monstrous enough, and of t's everywhere just makes things a lot worse. It does challenge your ability to follow along, because remembering which things are functions and which things are constants can get confusing. So that's something I want you to always pay attention to when we're looking at differential equations. Which things in the expression are constants and which things in the expression are functions of t. X, y, and phi are going to be the things that I use as functions most of the time. F and g are going to be functions more often than not. A, B, and C are going to be constants more often than not. And then let's consider x of t equals p1 phi1 plus p2 phi2. We can differentiate x prime of t. Well, derivatives of linear combinations work really nicely. You take the derivative of each function in turn. P1 is a constant. When you're taking the derivative of a constant times a function, the constant in front stays the constant in front. And then we'll have phi1 prime, and we'll have p2, and we'll have phi2 prime. And taking the derivative of that will give us x double prime of t, p1 phi1 double prime plus p2 phi2 double prime. And then plug that into the differential equation. A times p1 phi1 double prime plus p2 phi2 double prime plus b times p1 phi1 prime plus b p2 phi2 prime. Right? Why did I put b's, p's, and phi's in the same equation? And c's. Right? So we plug that into the left-hand side. Then we will distribute. So this is equal to a p1 phi1 double prime plus a p2 phi2 double prime plus b P1 phi1 prime plus B P2 phi2 prime plus C P1 phi1 prime plus C P2 phi2 prime. Next step, I'm going to rearrange things. I'm going to get all of the terms that have a P1 in them together, and I'm going to get all of the terms that have a P2 in them together. And I'm going to factor out the P1. So I have A times phi1 double prime, I have B times phi1 prime, I have C times phi1, which I introduced an extra prime into for some reason in the last step. There should be no primes on these two, sorry about that. But anyway, all three of those terms are multiplied by P1. I factored the P1 out. And then I'll do the same thing for all the P2s. A times phi2 double prime plus B times phi2 prime plus C times phi2 all times P2. And then, if I can use the right pen, and then look at what I have in these two sets of parentheses. A times phi1 double prime plus B times phi1 prime plus C times phi1. That's what you would get if you plug phi1 into the original differential equation. And since we know that phi1 is a solution to the original differential equation, we know that if we plug in and we get that left-hand side, it has to be equal to the right-hand side, which is 0. And the same thing with phi2. Phi2 is a solution. So when we plug in phi2 into the differential equation and we get that expression that's on the left-hand side, it has to be equal to the expression on the right-hand side, which is 0. And 0 times P1 plus 0 times P2 is 0 plus 0, which is 0. And since we got 0 out, we know we have a solution to the differential equation. All right? And so that's a rule that we can use. It's called the rule of superposition. Whenever we have two functions which are both solutions to a homogeneous differential equation, then any linear combination, constant times the first one plus different constant times the second one, or the same constant for that matter, that will always give you a new solution to the differential equation. And so that's what I want you to play around with. I want you to demonstrate that these two functions, phi1 of t is equal to e to the t, and phi2 of t is equal to t times e to the t. Demonstrate that these two functions are both solutions to the differential equation x double prime minus 2 times x prime plus x is equal to 0. Three's too many. All right. Then I want you to take two distinct linear combinations. X of t equals p1 times phi1 of t plus p2 times phi2 of t. Pick values of p1 and p2. Don't pick 0, that's boring, but pick two distinct pairs of values, plug them in, get two new functions, and demonstrate that both of those functions are solutions to the differential equation as well. All right, we know that it's going to work. Play around with it, put some specific numbers in, get comfortable with the idea of linear combinations, get comfortable with the idea of second order linear homogeneous ordinary differential equations with constant coefficients, and I'll see you in the next video.